Welcome back, everybody. Did you find a few more cases where your algorithm breaks and maybe even ways of working around this? So here's a short list of, and certainly not exhaustive, of some scenarios where your algorithm might have trouble and where things might go wrong. So one trivial thing is what happens if the exit is immediately where you're starting. So as in, you don't really need to search around, but you just go up and down or wherever you are and you have solved the level. Can your algorithm deal with that? Maybe, but maybe if you're first looking around and moving in a particular direction, you might actually miss the exit at the beginning. So that's kind of one of those cases where a human would run the algorithm and would think that, oh wow, this is really what's going on here. I don't understand this. This is so trivial to solve, and the algorithm doesn't do it. But if you don't explicitly think about it, then that might actually be a case where you at least don't find a very good solution, as in you might move around a lot and then eventually come back to the exit, which was right there all along. So all you really needed to go was, for example, down, and you're searching around the maze and then only in the end coming back to it. Here's another one that you might not have thought of. What happens if there's no exit? Is your algorithm going to terminate at some point? Is it going to say, well, I don't know where the exit is, it doesn't seem to be there, or I can't get to it, so I'm just going to stop and say, cannot solve this? Or is it simply going to keep going round and round in circles and then never stop, and you wouldn't even notice that anything is wrong necessarily? This may sound like a constructed scenario, so, it's a reasonable assumption to say that if you have a maze, that you gotta be able to reach the exit, but, bugs happen, so in the algorithm that generates this maze, there might be a bug, and in a particular case, you might really not be able to get to the exit. It might be more subtle than that, where you can actually get to the exit, but it is so hidden, it is so intricate, that there's so many things that you have to go through that your algorithm can't find it. And that's a good check to do for any algorithm. Is it going to terminate in every case? And in general, that is actually one of the most famous problems in computer science that you cannot solve. So you cannot simply write a program that will check for any other program whether it will terminate. This is theoretically impossible. But nevertheless, in practice, you probably want to do this, and you can, of course, check, okay, where does my algorithm actually stop? Where does it say that, oh, okay, I found the exit now, I've solved it, or I don't know what to do anymore? So that's something you can definitely think about here as well. Another thing that might come up, when you're looking around, when you're shining your light in the different parts of the maze, maybe there's something wrong there. Maybe you don't see something. Maybe you're shining your light at a weird angle or something like that, or there's a bug in the program so that, for example, you don't see the exit when the exit is there. What happens in that case? Do you come back to something that you have explored previously just to check it again and verify that what you've seen before is actually what's there and was not because of some weird angle of your light, and I don't know, it didn't penetrate a particular wall because that was too far away and the exit was right behind it? So really, that would have worked out well if you had seen it, but you didn't for whatever reason. Is that something that might trip up your program? Is that something that might cause it to, for example, never terminate? Something else to think about. Now, this is relatively abstract exercise, and you might be wondering, well, why did we do this? I mean, okay, no exit in the maze, is that really something I need to think about? Because hey, I mean, come on, okay, it breaks, but so what? Well, you would be surprised how often this comes up in practice, and as we talked about before, I'm sure you've all run crappy programs that just crash for no reason and take a day's worth of work with them, and you're like, oh my god, why did this happen? It's usually because of something like this, because a programmer simply didn't consider these scenarios, or maybe briefly thought about a scenario and was like, well, that's just never going to happen. One of my pet peeves is network access. So pretty much on every device, you have network access, be that through Wi-Fi or through a wired connection or through a cellular connection or something like that. But you usually have it, and it's usually pretty good. Now, if you don't have network access, particularly on a laptop, a lot of stuff just breaks. Probably won't even load. Maybe it loads, but it gives you loads of error messages because, ooh, I can't reach a server somewhere. And that is really annoying because, well, usually when you're in a situation like that, you're, for example, in Yellowstone, where you have no network connection. There's no way for you to get internet. And you just want this file that you know is saved on your laptop, but you can't get to it because the stupid program insists that it needs a network connection to get to the file that is actually on the laptop. That would be one of the examples where, if you as a designer of an algorithm, as a computer scientist, as a programmer, think carefully about what could happen and how you want to handle this, you could work around these problems, right? So you can simply say, well, okay, there's no network connection, no big deal. I will just see what I have locally, and for everything else, I'm going to tell the user that, well, sorry, I have no network connection, but at least you can access the things that are stored locally. And of course, there are many, many other examples of this. That, for example, you have a network connection, but it's really, really slow. And if it's really, really slow, maybe you don't want to do this automatic update download in the background that would take about a gigabyte of bandwidth, and that on the particular connection that you have would take like 8 hours and cost you $100 or something like that. Also things that you would think would be handled by programs, but in practice are often not. So that's why we're thinking about this, and that's in particular why we're trying to break our program deliberately. We're trying to find failure modes, even though those may not be realistic in the particular context that we are considering, but they may be in other contexts. And these may seem so abstract that you're really wondering, well, do I actually need to handle this? And the short answer is yes, because otherwise for your users, programs will break in interesting and exciting ways that they don't expect and cause a lot of frustration. Again, I don't really need to tell this. I'm sure you've been frustrated by lots of software, and it just doesn't seem to get better, right? It's just all this new software and it breaks in new ways. Okay, cool, that's interesting, but it's still really kind of frustrating. Exactly because of this. And that's why we're doing this exercise, and that's why always when you develop an algorithm, regardless of whether you want to then actually implement the program for it, you should think about when does it break, and if nothing else, just document that so that somebody who takes your algorithm and implements it, or a user of your algorithm, knows what to expect and also knows that you've thought about this, right? So this is really a reassuring sign if you get some software and it tells you, well, okay, if you don't have a network connection, then weird things might happen. At least that tells you that the programmer has thought about this, and that they weren't just like, oh, you'll just always have network. And of course, you can take that into consideration and maybe not run that particular program when you don't have a network connection. Okay, so I hope that was at least a little bit of fun. Also something very nice you can take back into the classroom, in particular because you can divide up teams, right? You can have one team develop an algorithm and another team trying to break it. And that might be a lot of fun in terms of the interaction going back and forth. And then you can switch roles and have the other team fix the algorithm and the first team trying to break it or something like that. So lots of possibilities on how you could do this in practice.